Let's continue our discussion on the assembly language instructions. This is lecture 7. We're going to talk more about data transfer instructions, and then we're going to start discussions on arithmetic instructions. First, again, we're going to do a very quick review on data and data transfer instructions. x86 data access can be from registers or to registers. Also, we can access data which is stored in memory. For registers, you can access an 8-bit value or 16-bit value or 32-bit value, all based on the name of a register. And for memory, data size is usually matching with the size of the register using the same instruction. And if not, we're going to use byte pointer, word pointer, or dword pointer to specify the actual size of the data. We talked about basic move, data transfer instruction, move. We can use registers, memory, or immediate values. If segment register is the destination, source must be a register. We also looked at sign extension and zero extension for move instructions. Here's a new one, new data transfer instruction, exchange. The mnemonic of this instruction is XCHG. This instruction will swap the content of source and destination. The format is similar to the move instruction. We're going to do XCHG D, S. So the operation is to swap the content of these two operands. So the content of source will be put into the destination, and destination will be put into source. Restrictions: memory can only be used as destination. Another data transfer instruction is to perform effective address computation and load the result into a register. The format is LEA destination, EA. The operation is to calculate the effective address of the source, which is typically a memory operand, and the effective address is going to be put into the destination operand. We have an example here, LEA SI, bracket 10H plus DI. So the addressing mode for this particular source operand is register relative. And the way to calculate the effective address, is to add this 10 hexadecimal to the value of DI. The sum of these two numbers is the effective address. Okay. And this LEA instruction will copy that effective address into this destination operand, which is SI in our case. Okay. So as a result, after this instruction is completed, SI will have the value of DI plus 10 hexadecimal. Next instruction is so-called load full pointer. Load full pointer instruction is to load contents of memory into both register and segment register. Okay, you will look at an example in the next slide, but the format of this load full pointer instruction is LXX destination, address. Now note that this XX is going to be replaced with the actual segment register. So you can have an instruction called LDS, and destination operand, source. Okay. Or you can have LES, destination, source. The operation of this instruction is the following. The destination operand, which is the D here, is going to have the content of the address, and the segment register XX, depending on which segment register you use, is going to have the contents of the address plus 2 if the destination is a 16-bit register, or address plus 4 if the destination is a 32-bit register. Okay, it sounds very confusing. Yes, indeed. So let's look at an example. So we have some numbers already stored in memory. Okay, and we have 1122 stored at this data segment address column in the table. Now, this uppercase identifiers, those are typically constant numbers used in assembly language program. So without knowing the actual value of data underscore seg underscore ADDR, we know that this number, a 16-bit number, is the segment address. And this init table is similarly a constant number, another 16-bit value, and that is the effective address. So what we're trying to show here is, in this memory, we have some bytes stored at address, data segment address, column, init table. Okay. And we don't really care about the exact value of these the symbols represent, but they are some value, and we use these values to locate these bytes. So we have a couple of move instructions, and then we have LES instruction. Let me give you, again, 1 minute to work on this, and to give you a chance to see what will be the content of those registers after these instructions are completed. Especially the first 4 instructions. Alright, let's look at the solution. The first instruction is move AX, comma, data segment ADDR. We know from the previous slide that this data segment ADDR is actually 1200 in hexadecimal. So after the first instruction, AX will have the value 1200. And then we have this move DS, comma AX. That instruction will copy the value of AX, which is 1200, into DS. And then the third instruction is move SI, comma, bracket init table. So this is a data transfer. Destination operand is SI. Source operand is this memory operand, which is located at DS colon init table. And DS, we know, has the value data segment ADDR, or 1200, the same value. So we will go into this memory map, and we're going to locate to this location, and we're going to load 2 bytes, this byte and this byte, into SI. Let me say it again. Because this SI has 16 bits, or 2 bytes, so we will need to load 2 bytes starting from this memory address, DS colon init table. Let's go to here. This is DS colon init table, and we're going to load 2 bytes. The way we draw this memory map is each row will have 2 bytes representing the adjacent values stored at that location. So this 11 is located at init table, and this 22 is located at init table plus 1. So in other words, this 22 is stored at higher address, 11 is stored at lower address for that word, bytes.
22 is most byte of the word. Why exactly because it's the right?
Because 11 is stored at address init table, 22 is stored at the next address init table plus 1, which is a higher address. Because we use little endian for x86, so 22 is the most significant byte of that word. So after this instruction is executed, we will have 2211, this word, loaded from memory and copied into SI. Alright, the next instruction is LES DI bracket init table plus 2. Okay, this gets very interesting. LES is to load something into ES register. Okay, remember that the LXX. So in this case, we have ES. So we're going to load something into ES. Now, what will be loaded into ES? Let's see. Init table plus 2. The brackets. We know we're going to load something. We're going to copy something from memory into ES. And also, we're going to copy something into DI because DI is the destination operand for this instruction. So even though you see only one destination operand, which is a DI, but in fact this instruction will update 2 registers. One is the destination operand, the other one is ES. Init table plus 2, we're going to use this as the effective address to find the number to load from memory. So let's look at this memory map. Init table plus 2, that's here. Okay? This is init table plus 2. And the next one is init table plus 3. And then plus 4 plus 5. Okay. Anyway, so we're going to start from this location here. We're going to first load a word into DI. Okay? So starting from here, we're going to load a word into DI. So what we're looking at is this 4433. These 2 bytes going to be loaded into DI. Okay? And remember, we need to update ES register. So after we loading F4433 into SDI, we're going to load another 2 bytes or a word into ES. And we're going to look at the next 2 bytes, which is 66F55. So 6655, this word is going to be loaded into ES.
That's the sequence first to load at the DI.
Yep, that's right. That's the sequence. So starting from starting from this address, we're going to first load 2 bytes into DI. After that, we're going to load the next 2 bytes into ES.
Where do we get this
04, okay. 04 is because we start from 02. We took 2 bytes for DI. So let's say we took these 2 bytes. And for ES, we need to start from this address, which is the init table plus 4. We actually move 2 because we started at 2. We plus 2, that's 04. Yes. Mm-hmm. So this plus 4 is because we started at plus 2. Okay? And we do plus 2 on top of this 02 because DI has 2 bytes. You need to do 2 bytes into this DI. If I change this DI to, let's say, EDI, and EDI takes 4 bytes. So you're going to start again from here, take 4 bytes, and for ES, here should be plus 6. And that comes from this 2 plus 4. Yeah, if I change this DI to EDI, that's a 32-bit value. So you always fill in the destination operand by using whatever number of bytes it needs to have. Then right after that, you take additional 2 bytes into the segment base. Okay, so what I was describing is if I change this instruction into LES EDI, comma, bracket init table plus 2. In that case, because EDI is a 32-bit register, so we will need to take 4 bytes from this init table plus 2, starting from this location. So you will see something like 66554433 loaded into EDI. Since we took 4 bytes, so this 02 here should plus 4 in order for us to get the value for ESI. So in that case, we're going to load the value from DS column init table plus 6, and we're going to take 2 bytes and put into ES. So in that case, ES will have 8877. Is this clear? Okay. Can you say that again?
What's the difference between ES and ESI?
There's no ESI. There's
Well,
ES.
there almost too, but there was no ESI that I was seeing
LESI?
ESI. EAX.
Oh, ESI, that's a extended source index register. All right, the rest of the instructions are obviously easier than LES one, right? So, for example, move AX comma in the table plus 6. So we just locate that to that location. So that's here. And you're going to take 2 bytes, put those into AX. So AX will have 8877. So the rest of the instructions are very similar, so I'll skip them unless you have questions. Alright, so that was the data transfer instructions. Starting from this slide, we're going to look at arithmetic instructions, including addition, subtraction, multiplication, and division. Addition and subtraction are the things we will cover in exam. We will not cover multiplication or division in exam. We're going to again look at the flags register. The flag used to indicate the computation result of arithmetic instructions or other instructions. All the arithmetic instructions set flags. Carry flag, CF, the carry bit out from MSB of addition or subtraction. OF is overflow flag. That's when the computation encounters a number that's out of range. And we have zero flag that indicates the result is a 0. So all these flags, if we have a 1 on these flag bits, that's an indication of the flag is set. So if we see a 1 on the ZF or 0 flag bit, that's an indication to say the previous instruction generates a 0 as the result. If you see a 1 on ZF, that indicates the previous result is a 0. Okay, that's the meaning of these flag bits. If it is a 1, that means that flag is set, and that has specific meanings. Sign flag is just the sign bit. If 1, that means the result is negative. If 0, that means a positive number. Parity flag, we're using even parity. So if you see a 1, that means you have even number of 1s in the number. AF is auxiliary parity. Those are carry bit between those 4 bit boundaries. All these flag bits are stored in flags register, and they are referenced in conditional instructions. For example, later we're going to talk about conditional branch instructions. So based on whether the arithmetic computation result, whether it's a 0 or not, a conditional jump will be taken or not taken. Addition instructions, ADD, add, destination, comma, source. The operation is simple. We're going to add these 2 numbers, put the result into destination operand. ADC is slightly different from ADD. In this case, we not only add destination and source, we're also going to add this carry bit. This carry flag, carry bit, CF. CF stands for carry flag. Sometimes I say carry bit. It's the same thing. So ADC, you're going to take 3 numbers: destination, source, and the carry flag. If the carry flag is a 0, then that's the same as ADD. But if carry flag is 1, then you can have the additional 1. The third addition instruction is INC, or increment. This instruction takes only one operand, and that's the destination, and is in fact used as source also. We're going to add the value of D, the destination, to 1, and then the incrementing the value back into the destination operand. Likewise, subtraction instructions have the following variants. Sub D comma S, that's the plain subtraction. So you're going to subtract source from destination. So it's D minus S. So you can subtract source from destination and put the result into the destination operand. SBB is the one that's going to consider the carry flag, CF. So not only we subtract source from destination, we also subtract carry flag from the result. And final result is going to be put into destination operand. The next one is DEC or decrement. The operation is just -1. The last one is negate. This is kind of multiply with -1. So you're gonna just change the sign of that number. And this is two's complement negation. So it's gonna be different, just flip the sign bit. It's gonna do the two's complement negation. So that the result after the negation is still two's complement number. All right, so we're gonna stop here. We're gonna have a break, and we're gonna continue with arithmetic instructions once we come back.